In this lesson, we will look into one of the Boolean rules called DeMorgan Theorem. DeMorgan's theorem are basically two sets of rules or laws developed for logic simplification purpose. These two theorems allow us to negate and convert the input variables from one form of a Boolean expression into another form of expression so that it can be manipulated for simplification purpose. This table shows a list of Boolean rules or Boolean laws that can be used to perform logic simplification. And for this lesson, we'll focus in this DeMorgan's law, which has two types. DeMorgan's first theorem states that two or more variables which are not or together, this is not or together, is equal to two or more variables that is inverted and ended together. Alright, so that's the first DeMorgan theorem definition. However, it's not limited to only two variables. It can also be implemented to unlimited variables. As you can see here, you can implement DeMorgan first theorem to an equation or expression that has this kind of multiple input variables, and it still gives the same output type like this. And it also can be implemented to a terms like this, not limited to single variable only. It can also be implemented to this kind of term, A, B, C, B, C, D, E, so on and so forth. And the output still follows the same two input variables theorem here. For the second DeMorgan's theorem, stated that two or more variables that is not ended together is equal to two terms that be inverted, inverse, and all together. This is the definition of a second theorem. And similar to the first theorem, the number of variables is not limited to only two. It can have unlimited variables, and the output is still follows like the definition of two variables. And we can also implement this second theorem to expression that have a term with more than one variable in one term, and still the output follows the same rules applied to two variables. This is another example of how the DeMorgan theorem can be applied into an equation with a multiple variable input. So if you can see here, we have 1, 2, 3 product terms which has been complemented together. So if we want to use a simple approach, we can actually assume each of the terms as a single variable. For example, A, B complement is equal to X, BC is equal to Y, and then ACD is equal to Z. So our initial Boolean expression will become like this. Then if we follow the basic Boolean theorem, supposedly the equivalent equation will become like that. So x complement and y complement and z complement. So our final expression after applying the first Boolean theorem can be obtained by replacing this x with its equation. So x will be a b bar, y is here b c, and z is a c d. All right, then we have the new Boolean expression. So based on this, if you look at this carefully, we still have terms that can be further separately using Boolean theorem. So we can actually apply a second Boolean theorem to this part. So by applying second theorem, we'll get this equation for the first term here, and for the second term we'll have this expression, and for the last term actually you can straight away apply this one, because based on Boolean rules, any variables that have been inversed for 2 times will become the original variable, which is a double inverse is equal to a. So ACD double inverse will become ACD. So this is how we can use a Boolean theorem to further simplify or separate the original expression. Like the previous explanation using the first theorem, for the sake of simplicity, we can also use the same concept, which we can replace the term which has more than one variables with a single variable like this, and then apply the second Boolean theorem so that we will have the equivalent equation of like this. So once we get this one, we replace the new variables with the original variables. So in this case, x is equal to a b complement. So once we get the equivalent equation, so we replace x with the original, which is a b complement, and similar for the rest. And we also apply another step of Boolean expression, Boolean theorem, since we still have terms that has been and not ended together. So we can further separate like this term b c into the b complement or c complement using the second Boolean theorem. Alright, let's have a look how we can actually apply Boolean theorem here to equation like this. So based on this one, we have two term, single term A and second term which is a bracket term A or C. So for us to make it easier, we can consider this is as x and with y, where y is equal to bracket term A or C. So this will give us, sorry, this is inverse, give us exactly the same theorem here. So the output will be x or y. So we can replace x with A and y with the A or C. So our result will be X or A or C inverse. Okay, so that's why we have the form here. And we can have another step, is we still have a long inverse which cover two variable here. So this time we apply second Boolean theorem so that we will have this result. Okay, so based on the Boolean rules that we shows in the table, we can actually factorize this equation to have this kind of equation where any variables that is odd with 1 is equal to 1. So any variable, no matter it is a inverse or non-inverse, so anything that is odd with 1 is equal to 1. So that's why we have 1 here. So our final equation is actually n with, and the last one is any variables n with 1 is equal to the variable itself. So our final answer will be A inverse. Alright, let's solve this second example. It looks a bit complicated, but it's not actually. So we can start by giving a name for single variables for us to simply solve this equation. So we can give x equal to A, y equal to BC, and z equal to AB. Alright, so this expression will basically become x or y inverse or z inverse, and we have a long inverse here. Alright, so I think x a b bar, sorry for that, a b bar is equal to z. So the next step is actually to break the longest bar. So we try to break this longer bar using, so this become, now it's become one term, this become second term. So what will happen is actually, so since this is an OR operation, so our next expression will be x or y inverse and inverse, and the OR will become n, and z inverse will have another inverse on top of this. Alright, so we have this equation. So the next is actually based on these identity laws, we actually have a very simple equation, x or y, and with, since z also has a double inverse here, and with z. So after this, you can actually replace the original value of x, y, and z respectively, so that you will have this equation. Okay, so based on this one, still have identity rules here. So these both will become A, and then there's another identity rules, any variable ended with its own inverse will become 0. So this one will make this, the whole term become 0. So then we apply another identity rules, A or with 0 is equal to A. So A B bar or with 0 will become to A B bar. Alright, so this is how we implement this DeMorgan theorems to Boolean expression. Alright, we have see a couple of examples. Lastly, I will leave you with this exercise for you to try yourself how to apply DeMorgan theorems to simplify Boolean expression. Alright, good luck and thank you.